Welcome back. Today's video is about the singular value decomposition. So let A be an m by n matrix, so m rows and n columns. And define A to be the Gram matrix A transpose A. So this matrix, of course, will be this is the Gram matrix, G-R-A-M matrix. That is an n by n matrix. And let me say that the rank of A is, say, R. It might be some number, no more than the number of rows or the number of columns. And that's the same as the rank of this K, the rank of the Gram matrix. They have the same rank. So now K, this Gram matrix, is positive semi-definite. That means all of its eigenvalues are non-negative. So I think that it's a good idea to name the eigenvalues. It will be useful for what we're doing next. So all of those eigenvalues are non-negative. That's a characterization of positive semi-definiteness. So if I name those eigenvalues lambda 1 through lambda r, and then there's some more, say lambda r plus 1 through lambda n, well, the first r of them are going to be strictly positive, r being the rank of k. Those will be positive, and the remainder, lambda r plus 1 through lambda n, they might be 0. Well, they are 0. And now if r is equal to n, then you're looking at a positive definite Gram matrix, and none of these are 0, but some of them could be. In that case, I'll call them lambda r plus 1 through lambda n. So what we'll do is define the sigma i's. Sigma 1 is the square root of lambda 1. Sigma 2 is the square root of lambda 2, and so on, all the way up to sigma r being the square root of lambda r. And again, I'm going to fix an ordering on the eigenvalues of k so that lambda 1 is at least as big as lambda 2, which is bigger than lambda 3, bigger than lambda r. These sigma i's, the square roots of the lambda i's, they are the singular values of A. That's the definition that I'm going to make. So here's an example. I take the following matrix, root 2 minus root 2, 1 over root 2, 1 over root 2. When I construct its Gram matrix, that's A transpose A. When you multiply that out, as you should be doing, you get the following. So I try to investigate what are the eigenvalues of this thing. In order to find the eigenvalues of a matrix, I need to take this determinant of the matrix minus lambda times the identity, and that will be a polynomial in lambda, and I'll find its roots. In this case, that polynomial is lambda squared minus 5 lambda. It's a lambda. 5 lambda plus 4. Its roots are 4. Lambda 1 is going to be 4, that's the biggest one, and lambda 2, that's the smaller one, that's 1. What that means is that my sigma 1, the first singular value of A, is the square root of 4, that's 2. And sigma 2, the second singular value of A, that's the square root of 1, or 1. So in addition to singular values, which I've just computed for A, I also want to compute singular vectors of A, which are just eigenvectors of K associated to these eigenvalues. So my first singular vector for A will be the first eigenvector for K. And we're going to compute that on the next slide. So I just copied that over. Now, this is the same A and the same K. I computed the eigenvalues, and the question is how to find the eigenvectors. So let's review briefly how to find eigenvectors for a matrix. So I first pick an eigenvalue. I already know what it is. I pick 4 as the first eigenvalue. I need to find a basis of the null space of K minus 4 times the identity, 4 being the eigenvalue for K. And if you compute what matrix K minus 4 times the identity is, that's minus 3 halves, minus 3 halves, minus 3 halves, minus 3 halves. And the null space of that is not very difficult to compute. It has a basis given by the vector 1 minus 1. So I can take v1 to be that vector. v1 is 1 minus 1, and I'm going to call this the first singular vector for A. The singular vectors for A are going to play a role in the singular value decomposition that we're going to do later on in the video. Similarly, let's review again to find an eigenvector for k with eigenvalue lambda 2. Since I know that lambda 2 is 1, all I have to do is find a basis for the null space of k minus 1 times the identity. And you compute what that matrix is. It's not deep. 3 halves minus 3 halves minus 3 halves 3 halves. The null space of that is spanned by the vector 1, 1. So I can set v2 to be 1, 1. That spans the entire null space, the eigenspace, the one eigenspace for k. So this is my singular vector for A with eigenvalue 1. Now, I want to be clear here that v1 and v2, these singular vectors for A, are not eigenvectors for A. If you multiply A times 1, 1, you do not get a multiple of 1, 1. Instead, these are eigenvectors for k. If you look in this case, the matrix A doesn't actually have any real eigenvalues. You need to pass through the complex situation to understand the eigen decomposition for A. It only has complex eigenvalues. Those are the roots of the determinant of A minus lambda times the identity. And if you compute what that is, and I think that you should, it's good practice, well, A minus lambda times the identity, if you compute the determinant of that, it's still only a 2 by 2 matrix, so you'll have a quadratic polynomial. It's lambda squared minus 3 over root 2 lambda minus 2, unless it's a plus 2. And the last thing that I want to say here is that if you take A times v1, you certainly then will not get 4 times v1. 4 is not an eigenvalue of A. Similarly, A times v1 isn't 2 v1. You don't get to use the singular value as an eigenvalue for A either. Okay, so I want to recall that the eigenvectors of a symmetric real matrix that have distinct eigenvalues are actually orthogonal. They're more than just linearly independent. They're orthogonal to each other. So I'm going to give you a short proof of this. Suppose that K is symmetric, a real matrix, so K is equal to K transpose. And the entries of K are real numbers. And suppose I have a couple of eigenvectors, say V, so that K times V is lambda V, and W, so that K times W is mu times W, where lambda and mu are different numbers. They are distinct from each other. And V and W are eigenvectors, so remember in the definition of an eigenvector, I insist that they be non-zero. So V and W are not zero. So to see that V and W are going to be orthogonal, first look at the following dot product. If you try to compute K times V dot W in the Euclidean norm, then, well, K times V is lambda V, and the form is bilinear, so I can pull a lambda out of that. Now, on the other hand, KV dot W is just KV all transposed times W, and I know how to push a transpose into a product of matrices. And I can rearrange the parentheses any way I like, because matrix multiplication is associative. Now, K transpose is equal to K, so this is V transpose times KW. But KW is mu times W, so this is V transpose mu W, which is another way of writing mu times V dot W. So what we've seen is that the left-hand side, lambda times VW, is the right-hand side, mu times V dot W. Or if you subtract, lambda minus mu times the dot product V dot W is equal to 0. But lambda minus mu is not 0, because lambda is different than mu. So it must be that V dot W is equal to 0. So, for a symmetric matrix, eigenvectors with distinct eigenvalues are orthogonal to each other. Their dot product is 0. Now, if I had two eigenvectors for this symmetric matrix that had the same eigenvalue, but they were still linearly independent, say they had the eigenvalue lambda, as long as v1 and v2 are linearly independent, meaning in this case not scalar multiples of each other, but you could do this with a larger collection of vectors, well, if they're linearly independent, then you can do the Gram-Schmidt process with them and orthonormalize them, if you like. So you can, at the end of the day, assume that, so you can prove that every symmetric real matrix has an orthogonal, or even better, orthonormal basis consisting of eigenvectors. So for distinct eigenvalues, they're already orthogonal, and within an eigenspace, you can use Gram-Schmidt to orthogonalize your basis of eigenvectors, which means that your symmetric matrix is not just diagonalizable, but is orthogonally diagonalizable. The change of basis matrix will in fact be an orthogonal matrix. Okay, this will be useful in the next slide. So now let me explain the algorithm for computing the singular value decomposition, which is the same as giving you a theorem that there is one. So let A be an m by n matrix, and suppose it has rank R. And step one, so for A transpose A, that's K, grab R vectors, Q1, Q2, up to QR, and assume that they are orthonormal. I've written orthogonal here, but it's important that your Q1 through QR be orthonormal. You need to normalize them. Orthonormal eigenvectors of K, A transpose A, the Gram matrix, which is an n by n matrix. So grab orthonormal eigenvectors of A transpose A. You can do that. That's what we just proved on the last slide. And take the ones that have non-zero eigenvalues. So kick out all the members of the null space. So, and I'm going to order them in such a way that the eigenvalues are decreasing. So the first eigenvector has eigenvalue sigma 1 squared up to sigma r squared is the smallest one, but they're all positive, r being the rank of A, which is the same as the rank of K. Now that I remember these are normal, let Pi be the following. I just take A times Qi and divide by sigma I for I running from 1 up to R. So you can always find the Q's, and therefore you can always find the P's. 3, the theorem, is that you can rewrite A as a product of 3 matrices. The first matrix has got the P's in the column. So P1 is the first column, P2 is the second column, and PR is the rth column. This is an M by R matrix. And this will be multiplied by a square matrix, an R by R matrix, that is a diagonal matrix. It only has the singular values of A on the diagonal, sigma 1 through sigma R. On the diagonal, 0 is elsewhere. This is an R by R square matrix. And finally, you'll have to multiply by a matrix with the Q's in the rows. So the first row is Q1, the second row is Q2, and all the way down to the rth row, that's QR. This is an R by N matrix. So the first matrix is going to be called, reasonably enough, capital P. The second matrix will be called sigma for the little sigmas, and the third matrix will be Q transpose, because I like to think of matrices having vectors in their columns, and this one has them in the rows. Now, this decomposition of A, which you can always find, is called the singular value decomposition of A. A didn't have to be square in order to find a singular value decomposition. That's an important point. Now, we're going to see an example of how to actually compute that in just a minute. But before I show you how to compute that, I want to point out that you can rethink of matrix multiplication as follows. So this decomposition can be thought of as take sigma 1, the number, times first column of P times first row of Q, plus sigma 2 times the first column of P times the second column of P times the second row of Q, and so on, down to the rth, sigma r times rth column of P times rth row of Q. Now I'll explain in class exactly why this works, but it certainly does. What this means is that if sigma r, that's the smallest singular value of A, is a lot smaller than sigma 1, like the ratio of the two things is a very large number, bigger than your machine precision, then your sigma r is sort of inconsequential in the way that A behaves. And in some sense, you can remove that last term, the sigma r times the PR column times the QRth row, entirely, and get an approximation of A that might behave better. Okay, so now let's do a very concrete example. Suppose that A and K are the following matrices, so write that down. It's pretty clear to see that the rank of A is 2. You could find that by row reducing if you want. Now the first step in this algorithm is to find the eigenvalues and the eigenvectors of K. Okay, well, we know how to do that. We've done it several times now. So I'm going to skip the details of that and just write them down. You can check for yourself that K times the vector 1, 2, 1 is a multiple of 1, 2, 1, and the multiple is 3. It's 3 times 1, 2, 1. And similarly, K times minus 1, 0, 1 is 1 times minus 1, 0, 1. Note here that those are orthogonal to each other. And finally, K times 1 minus 1, 1 is 0 times 1 minus 1, 1. Those are my 3 eigenvalues, and those are bases for the 3 eigenspaces. The first one's going to be called lambda 1, that's 3. Second one is lambda 2, that's 1. And the third one is lambda 3, that's 0. So those are the eigenvalues of K. I take their positive square roots to get the singular values of A. That is, sigma 1 is the square root of 3, and sigma 2 is the square root of 1, that's 1. Now I define Q1 to be the first singular vector normalized. So that is 1, 2, 1 divided by its norm. And so I compute exactly what that is. It's 1 over root 6, 2 over root 6, 1 over root 6, because the norm of 1, 2, 1 is root 6. So notice that I don't have to orthogonalize this with respect to Q2, that's the eigenvector for eigenvalue 1, normalized, because they're already orthogonal, which we proved they would be. We expected these to be orthogonal, and we're not surprised. So you normalize that vector, it's this. And now you can compute, so those are going to be the rows for Q transpose, and now to get P, you just have to take A times Q1 divided by sigma 1. If you multiply that out, you'll find it's nice, it's 0, 0, 1. For P2, it's A times Q2 divided by sigma 2. Multiply that out, it's also nice, 0, 1, 0. So remember that in the third step of the algorithm, you will write your A as a matrix P, with the P1 and P2 as the columns of this matrix, P1 and P2, times a matrix sigma, with the singular values sigma 1 and sigma 2 as the diagonal entries, times a matrix Q transpose with Q1 and Q2 as the rows. So we have all of the data for that right here. Let's just write it out. The matrix P is here. The matrix Q is this nice square diagonal 2 by 2 there. And the matrix, sorry, that was sigma, and the matrix Q is got the rows there, 1 over root 6, 2 over root 6, 1 over root 6, excuse me, 1 over root 6, minus 1 over root 2, 0, 1 over root 2. So I'm just putting the rows Q in place there. And that's the matrix sigma, and that's the matrix Q transpose. So here I've written it out a little more cleanly. It's the same calculation that we had before. The last thing I want to say is that you can write this as a sum of 2 different rank 1 matrices, root 3 times the first column of P times the first row of Q, plus 1 times the second column of P times the second column of Q. And you can check for yourself that that's correct, that this adds up correctly, and I'll show you later on in class why this works the way it does. So let's take a detour. Let's talk about an application of this algorithm to image compression. So the idea is that you should start with a photograph, let's say this one, which I found in my Dropbox. And, well, you should view it as 3 different photographs, 3 black and white photographs. So these are RGB values. You can just decompose it into 3. It's a sum of 3 photographs. Photos is spelled with an H. There. That's a representative black and white photo. And, well, you can really think of your photograph as a matrix now, because if for every pixel you have a gray value, let's say ranging from 0 to 1. So your photo is just a matrix full of numbers, and you can work with that matrix any way you like. So you can import it into MATLAB. It's not especially hard. You can find the command in the help file. So this particular matrix has 576 rows, and they are linearly independent. So what I'm going to do is import this matrix into my favorite math software and do a singular value decomposition on that matrix. What am I going to get? Well, I'll get another matrix, and I can turn that back into a photo. So what you're going to have is your matrix as a summation. The first singular value times the first column of your decomposition times the first row, plus the second singular value, blah, blah, blah. We've seen this before. Sigma, say, 576 times P, that's a P 576 and a Q 576. Got too excited writing ones. So this sigma sum 576 could be extremely small, very small, relative to sigma 1. It could be basically a bunch of random noise, a very small, useless data that I don't need to keep. So you can change M, approximate M, by chopping it off. Write M as a, just take the first, I don't know, L terms of this, where L is some number. L, write the L. L is some number between 1 and 576. If L is equal to 576, then you have exactly M. If L is less than that, you have an approximation of M. So let's see what happens when you do this process. So if you only take the largest singular value of the matrix, then you're approximating your matrix by just this rank 1 matrix, sigma 1 times the first column times the first row. It's not great, but it captures a lot of the largest play of light and shadow in the photograph. If you take the largest 2 singular values, so you're approximating by a row times a column plus a different row times another column, it's similar, a little bit better. Capture the block, the big block, the black block of the suit. If you take the largest 3, it starts to resolve even more. Again, this is just a rank 3 matrix. It's only capturing the largest brush strokes, if you like. Now, if you take the largest 4 singular values, it gets a little better. You start to see a little bit more detail. So with the largest 5, it doesn't look very much different than largest 4. At this point, we should just move fast forward. Let's look at the largest 10. That looks like a photograph. If you take the largest 30, it looks quite good, if a little bit fuzzy. And the largest 100 singular values, it's now indistinguishable from the original photograph. So what's the advantage of this? Well, if you write your matrix as an approximation, a summation like this, well, then you're really not storing all of the data that's in M. Instead, you're doing some pre-computation, and then you're storing these vectors P1 through PL, and you're storing the vectors Q1 through QL, and I suppose the numbers sigma 1 through sigma L, which is a lot less numbers than all of the entries of M. And you don't even store the matrices, the PIs times the QIs. You multiply those, the computer multiplies those together at display time instead. So this is a pretty decent storage savings, especially transmission savings, if you're sending over a small line. I want to point out that your M is realized as this summation of these sigma i's times pi qi's, I running from 1 to r, 2i transpose. And you can view this as sort of like a Taylor approximation for matrices. So only it's a finite sum, which is handy. So these small sigmas, I want to emphasize, the later sigmas are supposed to contribute a relatively or comparatively small amount of change to M. So you can approximate M by taking fewer of them. which is all I really have to say about image compression. We should move back to pure math. So let's make a definition. We've almost already defined this, but let's be careful. Suppose that A is an n by n matrix. Say it's non-singular. Well, even with a non-singular matrix, it could be very large, and some of the singular values might be very small. And when the singular values are very small, relative to the larger ones, it can be really hard to work with, because A will be something like very close to being a singular matrix. So small errors in calculation below the level of machine precision can lead to real difficulty in actually computing things with your non-singular matrix. So if you define kappa of A to be the largest singular value divided by the smallest singular value, that is going to be called the condition number of the matrix. And if that number is too big, then we'll say the matrix is ill-conditioned. If the number is small enough, then we're going to call the matrix well-conditioned. So if the condition number is quite a bit larger than 0, let's say that the condition number is bigger than the machine precision that you're working with, then even in if in exact arithmetic you could figure out the solution, maybe you don't have the resources to do that because you're looking at a 10,000 by 10,000 matrix, and your machine can't do it either, so you're in really a world of trouble. So for a singular matrix, we see this thing going on. For a singular matrix, we're going to define the condition number to be infinity. So the larger the condition number, the worse off you are. So let's look at a concrete example of this. Suppose that I start with, call it A hat, and it's a very singular matrix. It's going to be a 3 by 3 matrix full of 1s. So you can tell that this is a singular matrix and the rank is 1. You could row reduce it to a pretty boring matrix. Well, if you make a small error, or maybe your machine does, and adds, say, epsilon in the diagonal, then your new matrix, 1 plus epsilon 1, 1, 1, 1 plus epsilon 1, 1, 1, 1 plus epsilon, is now quite non-singular. You can verify that if epsilon is any positive number, in fact any number that's not negative 3 or 0, this matrix will always be non-singular. And so in principle, you could always solve systems of linear equations that had this coefficient matrix. But you can see that this is very close to singular when epsilon is small by looking at the Gram matrix. That's A transpose A. The eigenvalues of this are epsilon plus 3 squared and 2 copies of just epsilon squared. Lambda 2 and lambda 3 are epsilon squared, which means that the singular values for A are epsilon plus 3 and epsilon. So the condition number of A is the ratio between the biggest singular value and the smallest singular value. Remember, we're assuming that epsilon is positive here. So the condition number here is epsilon plus 3 divided by epsilon. That's sigma 1 divided by sigma 3. Epsilon plus 3 over epsilon is, well, the epsilon over epsilon is 1, so this is really 1 plus 3 over epsilon. And if epsilon is very small, then this is a very big number. You can easily make this bigger than your machine precision. So this is a way of quantifying, if you like, how close your non-singular matrix is to actually being a singular matrix. Now we're running a little bit long here, so I think that I'll stop there and see you in class.